Good afternoon, everyone. Welcome back to College Algebra. In the previous video, I talked about how to solve exponential equation, and I introduced two methods. The first method is to use equivalence property. The second method, I say that we have to use logarithm function. So in this video, I want to talk about logarithm function. This function will help you to solve exponential equation. The reason we want to learn logarithm function to solve exponential equation because there's a relation between logarithm function and exponential function. To be honest, they are inverse of each other because their graph, they kind of symmetric about the line y equals x. Okay, so in this video, we're gonna talk about more about a logarithm function. We're gonna investigate how the logarithm function and exponential relate to each other. Okay, so let's get started. Logarithm function. The same as exponential function, logarithm function also has the standard form. So, first of all, I want to talk about its definition and its standard form. So, the standard form of logarithm function is f of x equal to log. Okay, this is log. Well, the log concept is invented a pretty long time, I think about like 500 years ago, more than that. It's just a function. It's just it's like any other function, you know. And you don't have to know much about why we use the word log. Actually, it comes from the logarithm function, and you can look it up why we call this, but you just need to know at this moment that it's just a function. It's like rational function, exponential function. It's just a regular function. Okay. F of x equal to log base b of x. Okay. So this is the standard form of logarithm function. B. Okay. You see that I write b as a subscript. Okay. I don't write it on the same level as the log function. I kind of lower the letter b a little bit. This is the base. Okay. The x inside the parenthesis is the argument, right? It's the argument. Okay. Okay. So the log function, it might be increasing or decreasing. It's depending on the b value. Okay, it depends on the b value. If the b value is greater than 1, the b value is greater than 1, okay, it's an increasing function. So log is increasing function. Okay. And the graph of the log function at this time will be something like this. Okay. Okay. So now what do we know about this? You will see that the curve here is close to the y-axis. So this is y-axis, this is x. The curve is cut the x-axis at one point right here. And the curve is close to the y-axis. So in this case, the y-axis becomes the vertical asymptote. It means that the curve here, it never crosses the y-axis. It gets close to the y-axis, but it never crosses. Okay. So you see that if you go from left to right, the function is increasing. It's going up, and it keeps going up. Okay. However, if b is between 0 and 1, okay, we have decreasing function. decreasing function. Okay, we have something like this. Okay, it still cut the y-axis. Okay, oh, it still cut the x-axis. I'm sorry, but it never crossed the y-axis. So the y-axis is still considered as the asymptote. So it's still asymptote. And this is still also asymptote. Of course, because this is the very standard one, you know, the standard form. So the vertical asymptote is the y-axis. However, the vertical asymptote can be moved. It could be moved to the left or to the right. Okay? Then, if you move to the left or to the right, the domain and range will be different. Well, the range will be the same, but the domain will be different. But for this, okay, for this one, if we investigate the domain, okay, what is the domain? You see that the curve is lie on the right-hand side part of the coordinate system, right? We don't have the curve on the left-hand side, and it never crosses 0. So no matter what, it's increasing or decreasing, the domain is always greater than 0. It means the x value here is greater than 0. Okay? It's greater than 0. So the domain will be 0 to positive infinity, right? Not included 0, right? Because you see that it never crossed the vertical asymptote, the y-axis. Okay? How about the range? Well, the range will be easy, right? Because you see this keep going up, okay, and this is keep going down. For this one, it's keep going up, and this is keep going down, keep going down. So you see that for the range, we look at it from the bottom up, right? So it go from negative infinity to positive infinity. Okay. However, as I already told you, if the vertical asymptote, the y-axis, the vertical asymptote is not the y-axis anymore. For example, if it moves to the left or to the right, then the domain will be different. Okay, then the domain will be different. However, the range will be the same. Okay, I can give you the example. Example of log function. For example, over here I have f of x equal to log base 2 of x. Okay. The question is the base, the b value, can it be negative? No, it's never negative. So over here I may include it. B is always greater than 0. Okay, the base always greater. We don't have negative base. Okay. So this is a typical example of the log function. Okay. Or I can have something like this. F of x equal to log base 10 of x. You see, I'm writing very carefully. You see that the base and the subscript, I always write it lower than the log and the argument. The log and the argument is on the same level. However, the base is a subscript, I write it lower. Okay. So every time you have log base 10, you can write it as, you can throw away the base. You can write it as log x. So every time you write log x, it means that I know that mathematically that's log base 10. Okay? So don't ever miss the base unless you mean it log base 10. Okay? Or I can have something like this. Another function, f of x equal to lnx. Okay, what is lnx? Lnx is natural log. We call it natural log. Okay, remember this is the e number last time I mentioned in the previous video. Lnx, it means log base e. Okay. B is about, I don't know, you can put it into calculator, right? 2 point something, you remember I showed you last time. I just want to make sure. So 2.71. Okay, 2.71. It's the e. So if they write it like this, ln(x), then you know right away. This is log base e of x. Okay, but not a lot of people write like this. Actually, nobody write like this. Nobody write log base 10 like this either. So they write it like this or like this. Okay, and like this. Okay, for base 10 they write it like this. For base e they write it like this, and we call it natural log. However, for log base 10 we don't have the typical name for that. Okay, or I can have something like this. Or before I jump, I give you another example. We know right away that all the log function I give you here as an example, they have the domains from 0 to infinity. Okay, and for the range is also from negative infinity to positive infinity. Then what would be the function when we have different domain? I'm going to give you something like this. Example 2. For example, I have f of x equal to log. I can use base 2. However, the argument will be different. The argument like x plus 2. What does it mean? You remember we learned transformation function? If we add 2 to the x inside the parenthesis, it moves to the left or to the right? It moves to the left 2 unit, remember? We move to the left 2 unit. It means that the graph will have something like this. So this 1 unit, 2 unit. So this is vertical asymptote right here. Okay. And this is the b value still. In this case, the b value could be it must be greater than -2, right? It must be the argument. I'm sorry. Everything inside here must be greater than because you see the argument must be greater than 0. So the argument here is x plus 2. So x plus 2 must be greater than 0. So x must be greater than -2. That must be greater than -2. Okay. And the b value is 2. So it's greater than 1. So we know this increasing function. We're going to have something like this. I just sketch, okay? I just sketch. Something like that. Okay. And we just, if we want to know where to cut, okay, we call that the x-intercept. Right now we don't know, but in the next few minutes I will show you how to find x-intercept of the function, of the log function. Okay. All right. Okay. All right. So we know the standard form of the log function. When you learn log function, there's a principle. It's called the log principle. The log principle is very helpful. It will help you to find the output given a certain input. It can also help you solve log function. So I want to introduce the log principle and I want you to memorize this also. Okay? Log principle. And the log principle is so important that so I have to use the red color here. The log principle states that if y equal to log base b of x, see that? Then this is equivalent to, x equal to b to the y. Okay, it's equal to x equal to b to the y. So you see basically what you do is you keep the x and you kick the b value and you raise the b value to the y exponent. Okay, so the y over here becomes the exponent. Okay, this is called the log principle. Very important. Okay. Okay. And you see that given exponential form, I can convert to log, standard log form, okay? Or if they give you the log form, I can convert it back to the exponential form using the log principle. I can give you the example. Example 3. Okay. Write log expression in exponential form. Log function is one of the hardest functions, so I want you to stay focused with me, okay? A lot of students had that, but it's not really that bad. The thing that, because with my experience, I just think that because students don't memorize all the log formula, that's why you find it really hard. But as long as you memorize the standard form, you memorize the log principle, and you memorize all the property, the formula, then you should be okay. So I have log of 2 of 16 equal 4. And I want to write this expression here, this equation here, in exponential form. Okay. Of course, we have to use the log principle. We need to define the b value, the x value, and the y, right? Okay. So just think about this. And look at this. Log base b of x equals y. So b in this case basically b is 2, right? B is the base. 16 is x, right? And 4 is what? 4 is y. Then of course I can write it as exponential form easily, right? So this one will become what? It becomes x is 16, I keep it right. X equal to b to the y. So this is b. So 2 to the 4. Okay. Very easy. Very easy. You just need to learn this. You just need to memorize the log principle. Or I can have something like this. Log base 10, because base 10, so I don't need to write a base. The argument is 1 over 1000 equal to negative. So the y can be negative, okay? The y can be negative. However, the b cannot be negative. The x cannot be, the x must be greater than 0. Okay, in this case, the argument. Okay. So I have 1 over 1000. Okay, I know the b is 10. Okay, so how am I going to write? X is 1 over 1000. So this is implied 1 over 1000, right? Okay, 10 to negative 3. The base b, kick them up and raise this to the negative 3 power. Okay, let me do that. Very easy, huh? Okay. Alright, let's get back to the question I had before. I want to find the x-intercept here, or I want to find the y-intercept. Okay. So remember, when you learn any kind of function, you evaluate that function at certain value, right? You want to find the output given the input. You plug in the input into the function. Okay, and then you just calculate the output. However, for log function, it's kind of a little bit harder. When you plug the input into the function, in order to find output, you have to use the log principle. That's one of the ways. The second way is you have to use something called the Loc property. Okay, and there are many Loc property. Okay, I say many, but actually not about 10. You know, but you have to memorize it. Without Loc property, you cannot find the input or the output of the log function. You cannot simplify a log expression. You cannot solve log equation that we're gonna do in the next video. Okay. So in the second part of this lecture, I want to talk about Loc property. Okay. Loc property. And there's some property you have to memorize. Okay. The first property is log base b of 1 equals 0. Okay, for example, I have log base 2 of 1 is 0. 1 is the argument, 2 is the base. Okay, that's a log. That's one of the important property for log. Okay. The second property, log base b b equals 0 if the base and the argument the same. Okay, it will give you 0. For example, log base 2 of 2, oh not 0, sorry, give you 1. Okay, give you 1. Number 3, log base b of a to the c power. So a to the c power in this case is the argument. This is equal to c times, you can bring the c to the front. Okay, log base b of a. So you see again, I write very carefully. You see the base, it's a subscript, so I load them. I lower them, then it's lower than log of a. Okay. Example, log base 4 of 3 square is the same as 2 logs base 4 of 3. Okay. Number 4. Number 4. Number 4. If I raise b to the log base b of x, so b over here is the base of the power number, b over here is the base of the log of x, then this is equal to x. This is equal to x. Example, I have log base 2 of 2 to the third power is 3. Okay, basically you just need to bring x here, down here. So bring down 3 here, down here. Okay. Oh, I think I write it wrong, right? I write it wrong, I'm sorry. So 2 log base 2 of 3. So you see the base here and the base here the same. Then I just write number 3 over here. Just ignore what I just said like 1 minute before. I write wrong. So 2, 2, b, b, x, bring it here. 3, bring it here. Okay. So I should write number 3 down here. I'm sorry. So it's 3. Okay. Because this is considered as a power number, so the equal sign should be down here. Okay. Okay. Number 5. We can add two log together, log, but we must have the same base in order to add b of x plus log base b of y that equal to log base b of x times y. Okay. Okay. Or you can subtract. Number 6, log base b of x minus log base b of y equal to log base b of x over y. This is how I learn. I learn like this. Sum of the log is the log of the product. Difference of two log is the log of the quotient. Okay. So remember, the b must be the same in order to combine it like this. Okay. The base must be the same. Okay. Number 7. Log base a of b. Okay. Base b of a. A is the argument, b is the base. I can split it up into two log. Let's give you log base b of c times log base c of a. Okay. This formula is very important too. Okay. So next I'm going to give you an example how to use this property here to simplify a log expression. Okay. Okay. So let me give you example using the log property here to expand the log expression, or you compress the log expression. Okay. Example 1. I want you to write this expression as the sum or the difference as the sum or the difference. Okay. A. I have log base 2. Log base 2. The argument is z to the third power over x y to the fifth power. Okay. That's why I told you, exponent and log is they're very close to each other. They are related to each other because actually they are inverse of each other. I'm gonna put it as a remark later. Okay. So you see that everything inside the parenthesis is the argument. Okay, it's the argument. And you see that it's in the quotient form. And if it's in quotient form, you see that we can use the property number 6 here. I can split it up into the difference. Okay, so this base 2, I can write it as log base 2 of the numerator, right? X is numerator. Numerator here is z to the third power, so z to the third power minus log base 2 of x, y to the fifth power. Okay. Log base 2z to the third power, I can use this formula. I can bring c to the front. C in this case number 3. So I can write it as 3 log base 2 of z. Okay, minus. Okay, so over here x, y to the fifth power is the argument. Okay. And this is a product. And the product I can split it to the sum using the fifth formula here. So I can write it as log base 2 parenthesis log base 2, because when you split into the sum, you minus the sum, you have to put parenthesis base 2 of x. Okay, x times y to the fifth power plus log base 2 of x, of y to the 5th power. Okay. Let me erase this so that you not getting confused. Okay. So over here, the minus sign can distribute them. So we become 3 log base 2 of z minus, right, minus log base 2 of x minus 5. You can bring it to the front, right, using the formula over here. So 5 log base 2 of y. And here you go, we finished. We successfully convert this expression, log expression, to the sum or the difference. So all of them over here is the difference, so which is good. Okay. So all the formula you have to, you need to have it in your brain all the time. Of course, you can open the note, because right now from this time on you have the test 3 take home, right? You have final test take home. However, just think about it, if you have it in your brain, then it's easier to manipulate. Okay. B. I have something like this. Log. The same kind of question, okay? Log base 10, so I'm not writing base 10. Cube root. Okay. xy square over 10. Okay. So how we do this? Okay, so you see the log this is log base 10 and this is a cube root. Remember, any root we can bring it to the exponent. Remember this formula? M root of x to the n is equal to x to the n over m. Okay, we already learned this. Intermediate algebra. So this is cube root. So this I can write it as log of xy square over 10. Everything raise it to the 1/3. Because over here, the exponent of the whole thing here is 1 inside. Okay. M over here is 3, and is 1. Okay, the whole thing here is 1. Okay, it's an invisible one. Usually, x to the first power we never write, right? So right now we can multiply them in. So this is xy 2 to the 3rd power, right? Over 10 1 to the 3rd power. Remember the formula? X to the m raised to the n is x to the m times n. Okay. So 10 over here is 10 to the 1st power. 1 times 1 to the 3rd is 1 to the 3rd. And now is this a quotient next to y. So I can split it up into the difference. I use the number 6. So this becomes log base 10 xy raised to the 3rd power minus log base 10 of 10 1 to the 3rd power. And now I can apply log base a of b to the c. I can bring c to the front. So it will be 2 to the 3rd power, 2 over 3 log base 10 of x plus y. Okay. Bring it up, 1 over 3 log base 10 of 10. And log base 10 of 10 is log base b of b give you 1. So log base 10 of 10 is 1. So 2 over 3. This one we cannot do anything because log of the sum, we don't have the formula. We have log of the product. We have log of the quotient, but we don't have log of the sum. So I just leave it there. Okay. And log base 10 of 10 is 1. So this is my final answer. Okay. Okay, so you see that in order to do log really well, you need to memorize all the exponential formula. Okay, because there's a relation, as I told you again, there's a relation between the log function and exponential function. That's why you have to memorize all the exponential functions. It helps you simplify the log expression. If you don't know this formula, you cannot simplify it. Okay. In the third example, I want to give you the example that we have to use the log principle to evaluate the log function. Okay. And sometimes we have to use the Loc property. So either you can use the log principle to evaluate, or you can use the Loc property. You know, most of the time I use the Loc property because it's faster. Okay. Example. Okay. I want you to evaluate log function f of x equal to log base 4 of x at x equals 16. Okay. So I'm going to solve this. I'm going to evaluate this function at x equals 16 using the two methods, right? Using two methods for you to see. Okay. First method is I use the property. Using property. Okay. So if you want to evaluate the function, right, you just need to plug them in. You just need to plug the 16 in. So f of 16 equal to log 4 of 16, right? I replace the x with 16. It's the same thing as you do any other kind of function when you evaluate it. So for 16, if I use the property and I use the old exponential formula, 16 I can rewrite it as 4 squared, right? Okay. And remember the third property, I give you log base b of a to the c. You can bring c to the front, right? So I can bring 2 to the front. It's 2 log base 4 of 4. And log base b of b, base 4 of 4, if it is the same, it's give you 1. Okay, remember. So log base 4 of 4 give you 1. So 2 times 1 is 2. Okay, so you see that at x equal to 16, f of 16 is 2. You can find the output. So 16 is the input, 2 is the output of the function. Okay? But that is method 1. Method 2, you use the log principle. Okay, this is where the log principle comes into place. Okay, so how we use the log principle? The log principle is y equal to log base b of x, x equal to b to the y. Okay, so first of all, I write it down, log base 4 of x. Okay, and right now x is 16, right? X is 16, and you want to find y at x equal to 16. Then y equal to log base 4 of 16, right? Okay. Now we do the same as the log. This is b, this is x, so this is equal to, equivalent to, right? X equal b to the y, so 4 to the y, right? And we use the equivalence property to get y, so 16, I can change it to 4 squared, right? Okay, now you see that because the base is the same. You remember the equivalence property when we learn how to solve exponential equation? If the base is the same, we can set up the exponent equally. So this is equal to 2 equal y, and that. And you see that? It's the same. So you can use the log principle. Okay. Or you can use the property in order to evaluate the log function at certain value. Okay. In the next solution, in the next example, I want to give you a problem of how to find domain of the log function. And let's see how to find domain and how to find the y-intercept. Well, actually, find the domain. I already give you an example already, right? I give you the f of x equal to log base 2 of x plus 2. Okay? So, find domain of log function. Okay. Strategy. It is setting the argument greater than 0. Okay. For example, if I have f of x equal to log base 3 of x plus 2, the argument is everything inside the x plus 2. So you set x plus everything inside the parenthesis. I'm sorry. So you set the argument greater than 0, and you solve for x. And from here you can derive the interval notation. -2 to infinity. So that's it. Okay. And you do the same, you use the same strategy when you find the domain of any log function. Okay. How about finding the output? Not finding the output, finding the x-intercept. Find x-intercept. Point of log function. Okay. And what if I have something like this? F of x equal to, again, I'm going to use that log base 3 x plus 2. And I want to find the x-intercept point. Okay. The x-intercept point is the point where the curve of the log function intercept the x-axis, right? In order to find the x-intercept point, you set f(x), you set y equal to 0, remember? So you set this equal to 0, 0 equal to log base 3, x plus 2. Then you use, again, log principle. So this is your argument here, this is your y, this is your base, so this is x plus 2 equal b to the y, so 3 to the 0, because I using log principle. Okay, 3 to the 0 give you 1. Okay, so your x will be -1. Okay, then your x-intercept point will be -1, 0. Okay, it's very easy. All right. Let me see how many minutes left I have. Okay, so I still have 15 minutes for this. Because I set up the camera and I did, the camera just can record half an hour. So that's why I have to keep checking the amount of capacity of the scan disk. Make sure they have enough space to record the video. Okay, so I have 15 more minutes. I'm gonna give you more example of how to use the Loc property to write log as the sum or the difference. Okay, or sometimes we can write the sum of difference as a single log. Okay, example. If the question that give you the log as the sum or the difference, you can rewrite it as the product or the quotient. Okay. write the expression as a single log. Okay. So this is what I have. I have 1/2 natural log ln x, okay, plus ln x squared plus 1. Oh, it's minus, I'm sorry. Minus ln x plus 1. So the question is in the sum in the difference form, okay? And I want to rewrite it as the quotient and the product form, as a single log. So we have 3 log, here natural log. We have to rewrite it as 1 log only, okay? So remember, if we have the sum, we can rewrite it as the product. However, we need to bring 1/2 up here. We can bring it back. So this is equal to ln of x 1/2. Okay, I bring 1/2 back to the exponent, plus ln x squared minus 1 minus ln x plus 1. So I combine these two, because this is sum already, I can read it as the product. So this is equal to ln. But before doing that, x to the 1/2 is square root of x. Okay, x to the 1/2 is square root of x. Plus ln x squared minus 1 minus ln x plus 1. Then this is the sum, give you the product. This gives you the product. So square root of x times x squared minus 1. See that? It's a product. Okay, the sum gives you the product, remember? Minus. And the difference gives you the quotient. So I can write this as ln. This minus this, so this will be as the numerator on the top, so square root of x squared minus 1, over, this is the bottom, x plus 1. So we successfully convert 3 log to 1 log. It looks like we done, right? Because that's what the question asks you to do. However, in order to beautify it, you say x squared minus 1, you factor them, give you x plus 1, x minus 1. Okay. Then you see this, we can cancel. Then my answer, our final answer will be better. Square root of x minus 1. 8. Okay. So that is the purpose of or the property. It helps you to simplify the log or help you to expand the log. Okay. Another purpose of property of the log property is to help you to solve log equation. Okay. And as long as you know all the properties, you should be okay for log equation. Okay, but that is what we're gonna do in the next lecture. So that's all for today. Oh, before I'm doing that, before I stop, I remind you the remark I want to give you, right? So you see that there's a relation between the log and exponential function, because every time you use log, there's an exponent formula come into place, right? So there's a remark you need to remember. Log function and exponential function are inverse of each other. Okay, it means that if you graph two curves, okay, if you graph two curves, one curve is log, okay, this is log, and the other curve, okay, and the other curve is exponent. They always symmetric about the line y equals x. So there you go. So this is f of x equal to a to the b to the x. Sorry. Okay. So they are inverse of each other. And because they are inverse of each other, they are symmetric about the line y equals x. Okay. Alright, so that's the most important thing. One of the most important things. That's why every time you do log, there's exponential formula come into place. Okay? And that's why when we solve exponential equation, we can use log function to solve it. Okay? So that's all for the lecture regarding the log function. In the next video, I'm gonna show you how to solve log equation, and we will learn how to solve exponential equation using the log function. Thank you so much, and I'll see you next time. Bye bye.